Okay, you should have just viewed the video on surface features and how to forecast for the movements of fronts using both the surface and 500 millibar chart. And let's take a look at your syllabus, because now we're going to move from fronts. Now keep in mind we're building our forecasting tool, but this week we're going to talk about moisture and forecasting winds. So to do that, let us go to our list of maps here, maps to use for forecasting. And if I want to look at moisture, and again, let's go to our weather forecasting assignment and see which questions have to do with forecasting for moisture. And I'm going into the 0-0 forecast. And so question 13 actually talks about moisture. So we need to know a little bit about how to interpret maps for moisture. We're also looking at predicting wind speed and wind direction. You see that in questions 10 and 11 of your forecasting exercise. So let's go down here and look for, let me go back here just a moment. Again, I'm looking at question 13 for moisture. And in fact, if you go right here under this helpful link, how do these factors influence precipitation? For moisture, you see right here, if you have at least 70% relative humidity, and we'll talk about what relative humidity is later down the road here, very shortly in the next week or two. But usually you have overcast conditions with 70% relative humidity. And at about 90%, there's a good chance that precipitation is occurring. So for the forecasting exercise, what it looks for is the middle ground. It looks for a relative humidity of at least 80%, and we'll consider this a favorable value for the production of precipitation. Recall, to have clouds and precipitation, we have to have two key ingredients. We have to have sufficient moisture, and that should make sense, and a way to lift that air. Now, the reason why lifting air is important in producing precipitation and clouds, we will talk about later in this course. So, if we have a relative humidity greater than or equal to 80% at 850 millibars, recall that 850 millibars is approximately a mile above our heads into the atmosphere, at one of the times, 12Z, which recall for summer months is 7 a.m. 0Z would be 1 p.m. And I'm sorry, not 1 p.m., 7 p.m. 0Z is 7 p.m. and 12Z 7 a.m. the next day. So if I'm sitting here, let's say on a Saturday, getting ready to make my forecast, I want to see, or I want to evaluate maps of moisture to see if for Sunday, which is what I'm forecasting for, 7 a.m. there's at least 80% relative humidity, or at 0Z on Sunday, which would be 7 p.m. that evening on Sunday, a day into the future, or at 12Z, which would be Monday, the following day. So if any of those times show a relative humidity of at least 850 millibars of 80%, then we say that's sufficient moisture. And you can click on this link here for moisture supply, and we've got a nice little PowerPoint slide, and you can click through there. And again, this is a resource for you to be able to use, and so I would encourage you to use that. So if we go back and look at the questions in terms of sufficient moisture and winds, but let's concentrate on moisture right now. So I'm looking down here at 850 millibar map to analyze for moisture. In other words, the dew point depression is already calculated for you in this particular link. And for sufficient moisture, we're looking at a dew point depression of 5 degrees Celsius or lower. Now, dew point depression, recall, is the difference between the temperature and the dew point temperature at 500 millibar, or I'm sorry, at 850 millibars. So if I were to click on this link right here, and these are station models, just what you finished last week in your exercises. So notice this is at 850 millibars, about a mile up. Notice this is for 7 a.m. Saturday, June 4th, 2016. So if I look at Omaha, which is the nearest station to us, notice that I have a temperature of 13 Celsius. Let me see if I can blow that up a little bit more here. So at Omaha, the temperature is 13 degrees Celsius, and the dew point depression, they already calculate this for you on this particular map, is 10. So the difference between the temperature and the dew point temperature is a 10 degrees Celsius spread, which means the actual dew point temperature at Omaha is 3 degrees Celsius. So a 10 degrees Celsius spread between the temperature and the dew point temperature indicates dry air. Now if we look a little bit further, let's go to the north here, Minneapolis. Notice that the temperature is 11 degrees Celsius, and the dew point depression, not the temperature dew point, but the dew point depression, the spread between the temperature and the dew point temperature is 5 degrees Celsius. And so that would be considered moist. If I go over here to, I think that's Aberdeen, South Dakota, notice the dew point depression is 3. So the actual dew point temperature would be 7. So the spread between the temperature at 850 millibars and the dew point temperature at 850 millibars, which is 7, has a 3 degree spread. Now you'll notice if we go back here under the maps to use for your forecasting, I have two 850 millibar links. This one already has the dew point depression calculated for you. And notice says this is question 13 in the forecasting assignment. So I go through, I give you links, and I tell you which questions go to which links. So this should really help shorten up looking for maps and charts for you. Now if I look at this 850 millibar map, it gives me the temperature and the dew point temperatures. Okay, not the dew point depression. So let me increase this. So we see right here, remember we talked about up in Minneapolis, the dew point depression was 5. Well, that should make sense because the actual temperature at 850 millibars is 11, and the actual dew point is 6, which means there's a 5 degree spread. The dew point depression is 5. So this station would be considered moist. Over here in Davenport, temperature is 13 degrees Celsius. The dew point temperature is 8 degrees Celsius. That is a 5 degree spread. So again, that would be moist. I just think it's easier if you use this particular one, this particular link, because it already does the calculations for you. So we'll pull this back up. We'll look over at Davenport and notice the actual temperature is 13 degrees Celsius. The dew point depression is 5. Now, another thing to look at, this is a stagnant shot, okay, a shot in time, a picture in time of the 850 millibar surface at 12Z this morning. You'll also notice that we have wind speed and wind direction shown on these station models. So we look back to our west, and you notice we have northwest winds. And you see these pools of moisture. Now there's a legend down here that's relative humidity. Light green means relative humidity is anywhere from 70 to 80%. A little bit darker green is 80 to 90%. So anything slightly darker green and really dark green means we have sufficient moisture. So if I'm making a forecast for Des Moines for tomorrow, Notice I have winds coming out of the northwest. See, this is a northwest wind at 25 knots. This is a northwest wind at 35 knots. So I've got a plume of moisture here, this deep green and this lighter colored green, coming in from the northwest. So what does that tell you about 24 hours from now? Well, we might have another area or another blob of moisture moving into Iowa. So you not only look at the still shot, the stagnant shot, but you look at the winds to see how things are moving. Let's look to the south. We see large areas of 80 to 90% and some 90 to 100% down here. Notice the winds are out of the south and southwest here. So these plumes of moisture are moving up into Missouri. We've got a plume of moisture moving down into Iowa. Somewhere over the Ohio Valley, these will probably merge, and you'll probably see large areas of precipitation continuing to break out over the upper Ohio Valley. So the key here is when you're forecasting for the next day. Okay, if you're sitting down, today's Saturday, for example, you're sitting down today and you're forecasting for sufficient moisture at 12Z on Sunday, or 0Z, which is Sunday evening, or 12Z on Monday morning. If any of those three times has a relative humidity of at least 80%, then for question 13, you would mark as sufficient moisture. Again, you have to look at these wind directions and wind speeds and see how things are moving, because this is just a still shot, a snap in time, like I've said before. Now, notice back here over the west, northwest winds, large dew point depressions, 13, 14, 17, 18, 17. It's just dry air back here. And notice the winds are coming in from the northwest over here, over by the Rockies. And so you're bringing drier air from Canada down into the U.S., the western U.S. So the moisture is really, you could just basically draw a line north to south, halfway across the U.S. Moisture from the south is moving this way because the winds are out of the south, southwest. We have a plume of moisture up here to our north that's moving in from the north. And so that is a simple way of analyzing for sufficient moisture. Now the next item we'll look at is how to forecast for wind. Because if we go up here to our forecasting assignment on ClassNet, you'll notice down questions 10 and 11 have to do with wind. And notice that we're forecasting for wind speed at 18Z, that would be the next day. So if I'm sitting here on a Saturday, for example, as I'm recording this module, it is a Saturday afternoon, I'm forecasting for 18Z winds tomorrow on Sunday. Recall that 18Z during the summer months is 1 p.m. So I'm forecasting for wind speed at 1 p.m. If you're viewing this video module during the fall and spring, then 18Z would be noon. But as I'm sitting here today during the summer, I'm forecasting for 1 o'clock wind speeds. So there's a helpful link here. How is wind speed determined? So how does the forecasting exercise look at or grade for forecasting wind speed? So 1 knot, which is basically 1 nautical mile per hour, is about 1.115 miles per hour. So if we're looking at 10 knot winds, because recall that the station models are shown in knots, if you want to convert that, well, we use knots when we're referring to wind speed. But if you want to look at miles per hour, you would multiply that 10 knots by 1.15, and you'd come up with 11.5 miles per hour. So when we're talking about basically anything 20 knots or less, we can use these interchangeably. Beyond that, let's say if we get to 30 knots, then we're really talking about a 35 mile per hour wind. So the criterion used for a correct wind speed is if you have so let's say I forecast a wind speed for Des Moines, let's say 15 knots, and the actual wind speed is 10 knots. Well, there's a plus or minus 5 value. So if the actual wind speed is 10 knots tomorrow, anything from 5 to 15 would be marked as correct. So you don't have to get this exactly correct. You have a plus or minus 5. Now, most days during the summer, now not all days, but quite a few days during the summer, your winds are going to be roughly anywhere from 5 to 15 knots on any given summer day. So let's say, for instance, you forecast for 8 knots, and the actual wind speed is 15 knots. So anything from 10 knots to 20 knots is marked correct. You're going to miss that because you predicted 8. But let's say, for instance, the actual wind speed for tomorrow was 8 knots. You predicted 8 knots. You got it exactly right. However, let's say the wind speed was actually 5 knots for tomorrow, and you predicted 8 knots. So if the actual is 5, you predicted 8. Anything plus or minus 5 from the actual, 0 to 10, would be marked as correct. So I hope that gives you an idea about how that works. Now let's here's some examples of wind speeds. You've got a link here. There's a lot of helpful links back here. So if we click on Wind Help here, I have some PowerPoints here to kind of give you an idea to go through, to look at. So I encourage you to use these to help assist you. I'm going to go back here just a moment. So some examples of wind speeds you see here. We've done this with the station model. So this should make a lot of sense to you at this point. 60 knot wind. Notice that in miles per hour, you multiply that by 1.15. That would be 9. So that would be a 60 knot wind is an actual 69 mile per hour wind. That's why I'm saying anything over 20 knots, you want to do the calculations. Anything less than 20 knots, you can use miles per hour and knots interchangeably. Okay, so where do you look at? Okay, we're making a prediction for wind speed 18Z tomorrow. Well, lo and behold, under maps to use for forecasting, notice I have right here this link here. This link will help you with questions 2 through 13. And notice we have questions 11 and 12 having to deal with winds. So if I click on that, notice at 20Z on Saturday, which would be, let's see, 3 o'clock, 3 p.m. on Saturday afternoon, we see that the wind speed at Des Moines, see if I can get this a little larger for you. The wind speed is a single barb here, a full barb, so it's 10 knots. But if we go back to 18Z, okay, a few hours ago, 18Z, you saw the actual wind speed was 15 knots. So if you were sitting down yesterday on Friday evening, June 3rd, making a forecast for today, and you put 10 knots, your prediction would be correct because the actual wind speed plus or minus 5 is marked as correct. So if you had anything from 10 to 20 knots, you would have that correct. And you notice back here in the upper plains today, we actually have some pretty windy conditions. So this is one of those days where it's actually beyond what you would normally expect. 10 knots over northern Minnesota, 15 knots over the Dakotas, 15 knots over Nebraska. And so you see it's quite windy. And you also notice the winds are out of the northwest. So if the winds are out of the northwest, they're currently 15 here. And think about this. If you're forecasting for 24 hours from 18Z, okay, and the wind speed is 15 knots throughout here, and they're coming out of the northwest, we could just do a simple calculation to see how far back the wind speeds are coming from. So I take 15, let's just make it miles per hour, we can use that interchangeably, times 24 hours. Notice the hours cancel out, okay, because I've got it in the denominator here and in the numerator here. So 24 times 10 is 240, 480, so this is 360 miles that the winds will travel from the northwest. Do you see how I got that? I used the current wind speed, and I look back to the northwest because that's where the winds are coming from. And so it's like if you got into a car and you drove from the northwest down to Des Moines and you were averaging 15 miles per hour. In 24 hours, you would have driven 360 miles. So if I go back here, and basically from west to east is roughly 300 miles, but I go back the length of Iowa, about 300 miles, the winds for tomorrow will be coming from the Dakotas, basically north-south Dakota, right along the border. So if I were forecasting for tomorrow, I would forecast for northwest winds and continuing at about 15 knots. However, I want to look at some other items than just the station model, but at least that gives us an idea. Now, if a front comes through, if it's a warm front, the winds will change from the north to the south. So if you've got fronts coming through anytime in that 24-hour period, using this method of forecasting may not be the best way to do it. So let's look at, here's another link I have under maps to use for your forecasting. I have a surface map which works with questions 2 through 13. If I click on that, Now from the last video or a couple of videos before when we were talking about surface features, notice these white circles are what we call isobars, lines of equal pressure. And the way this works, you can count the number of isobars across Iowa. So we have one isobar here, one isobar along the western border, and on average, each of these isobars are akin to about a 5-knot wind speed. So you take the 5-knot wind speed times 2 isobars, and you can say currently about 10 knots as of the time this map came out. Let's see, and roughly looks like about a half an hour ago. So 10-knot wind speed. And also, look back to the northwest because we know winds are counterclockwise around low pressure, and so our winds are going to continue to come out of the northwest. So this is a map. When I'm looking at this surface map, this gives me an idea if there are any fronts, the locations of high pressure and low pressure, and I know winds are counterclockwise around low pressure, and wind direction is the direction the winds are coming from. So they're coming from the northwest. Notice I have high pressure out over the Rockies. Winds are clockwise around high pressure. So again, those are coming from the northwest over Iowa. And so I look back here, and so if the winds are coming from the northwest over the next 24 hours, I look back here and count the isobars roughly across 300 miles. Because west-east across Iowa is roughly 300 miles. And so again, I count 1, 2, or 1, 2. So 2 isobars. So we don't have a lot of isobars, which means winds are going to be lighter. So for tomorrow, I would forecast for 10 knots. So if I'm forecasting for 10 knots, I'm hoping the winds are anywhere from 5 to 15 miles per hour. Okay, so now we'll talk about wind direction here in just a moment. Let me go ahead and close this up. Now, if we go back at wind direction, so we also have to forecast for wind direction at 18Z. So we look at the link here, what determines wind direction? In other words, how does the computer forecasting exercise grade for correct wind direction? And it would be better just to show you. Let me just back up here. So when you're looking at wind directions, you can look at this as a station model. So you've got north, northeast, east, southeast, south, southwest, west, northwest. So let's say tomorrow we forecast for a northwest wind. The winds are coming from the northwest. And let's say the winds actually end up being out of the north. So if the actual winds are out of the north, if you put north, northeast, or northwest for your forecast, that'll be marked as correct. These are octals, 8 spaces on this particular circle. Let's say, however, you predicted west winds. So let's say we predict west winds for tomorrow. And the actual winds were southerly. Now they won't be tomorrow just by looking at the maps. But you predicted west. The actual wind direction tomorrow was out of the south. So the computer program for the forecasting exercise says a southerly wind or a southeast wind or a southwest wind, if you predicted any of those three, would be marked as correct. So what the program looks at, it looks at plus or minus 1 octal. So if the actual wind direction is south, it'll mark the question correct with south, southeast, or southwest. So it's a plus or minus 1 octal. And again, it talks about it up here. It's represented by 8 equally spaced compass points, octals. And correct if it's within plus or minus 1 octal, which is what I just showed you. And they give some examples there. So let's talk about some maps that we can look at for wind direction. Now this is question 12, so it's the same 2 maps here. We can look at a station model. And so we can see that the current winds are out of the northwest. So if I was just looking at this, I've got some southwest winds over here, southerly winds, but the general wind direction is out of the northwest, out of a large portion of the central U.S. So this will be pretty easy to forecast for tomorrow. I'll predict northwest winds. But again, another map that I have a little bit more confidence in is the surface map, because it shows the locations of the lows and highs, and I know wind directions around lows are counterclockwise, wind directions around highs are clockwise. And so I know that we've got northwest wind here, northwest wind out here around highs. The nearest, there really are no fronts out to the west, and these fronts will continue to move off to the east. This will be a pretty easy forecast. However, if you're looking at, let's say, Buffalo, which I think is, or actually Cleveland, which is somewhere right in this area here, today they have winds clockwise with a high out of the northeast, okay, out of the northeast. But as this front continues to move during the day toward them, then winds around low pressure are southeast, so there are southwest, and so their winds will switch from northeast to southwest as we head into tomorrow. So if you've got a front in the area or moving toward you, then what happened today more than likely will not happen tomorrow. That's why it's important to know how these fronts move. And that's why in the previous video module we talked about how to move fronts, surface lows, surface highs, using the 500 millibar map. We have to know how these fronts move, because if they're moving into your area, that's going to switch the wind direction and more than likely the wind speed as well. Okay, I hope you've found this particular video module helpful for you in forecasting for wind speed and wind direction.